Hi, I'm Lia Talozzi. I'm here to walk you through my current work at the University of Bordeaux, entitled Latent Disconnectome Prediction of Long-Term Cognitive Symptoms in Stroke. A stroke occurs when there is a cerebrovascular injury in the brain that may occur in the posterior, medial, or anterior cerebral artery. Thanks to neuroimaging techniques, it's possible to delineate in vivo the stroke lesion. Here, magnetic resonance imaging that allow us to appreciate the different contrast caused by the stroke lesion. Stroke symptoms mapping have a long history, starting from the association with the localization of the stroke in the brain to the association with the white matter disruptions. Here we manually delineated the stroke lesions and we used the normative dataset of the Human Connectome Project 7 Tesla to reconstruct whole brain tractography. Tractography was filtered according to the stroke lesion, obtaining the disconnectome, so the streamline passing through the stroke lesion. Using low dimensionality reduction techniques, we obtain a configuration to summarize the variability of the disconnectomes obtained. Then, in this framework, we run correlations with neuropsychological scores acquired at 1 year to predict the scores for new patients. Then, a white matter atlas reported the correlation between the risk territories in the embedding space with the localization in the white matter. Then we deployed a web application where it's possible to run online freely the model for new patients. Here the patient cohorts analyzed that were two, one acquired at UCL, the other at Washington St. Louis. Here, the data set divided in data sets 1, 2, and 3. MRI was acquired within 1-2 weeks after the stroke onset for all the patients, whereas for dataset 2 and 3 acquired at Washington St. Louis, neuropsychological scores were also available. 86 acquired 1 year after the stroke onset. The method used for the low dimensionality embedding was the UMAP method, Uniform Manifold Approximation and Projection. UMAP was run for dataset 1, the largest one, 1,343 stroke patients, and we obtain a disconnectome morphospace. Here, 3 patients where you can see in black the lesion localization delineated and the probability map in a red, yellow intensity map reported the probability across the healthy controls of the disconnectomes. And here the UMAP shaped that we obtain, where the patients are characterized by 2 coordinates, coordinate 1 and 2. The symmetry of this shape was due to the laterality of the stroke lesions in each hemisphere. The neuropsychological scores acquired at 1 year were 86 for dataset 2 and 3. Here are summarized according to different domains, so motor function, language, verbal memory, visual-spatial attention and memory, sickness, and pain. Here's some illustration of the scores acquired. So, grasping, pitching, 9-hole tag replacement, animal fluency test, Boston naming of the different pictures, and for visual-spatial ability, the Posner test. Then we obtain what we called a composite morphospace. So to each coordinate in the morphospace, the different scores acquired were reported. Here you can see for the left and grasping how the lowest scores starting from 0 are clusterized in a specific area of the morphospace. Then we run the pixel-wise correlations, and here you can see the risk territories delineated for R highest than 0.2 in a module. And these allow us to obtain a formula to predict the new patient neuropsychological scores. In this formula, we have the principal component analysis scores that summarize the neuropsychological variability in the different risk territories. And then the formula was trained using the dataset 2. And as outcome, there is the neuropsychological scores obtained. Then the white matter neuropsychological atlas was obtained, correlating the risk territories with the area in the disconnectomes. In panel A, you have the label according to the different scores that achieve the highest correlations, colored by the different functional domains. In panel B, we have the effect size map onto the white matter, and you can see how in the left hemisphere frontal connections, the highest effect size was obtained. Then in panel C, the versatility map, so the overlap between the different scores and the localization in the morphospace, and the highest scores were reported in the right hemisphere. Then how to sample model validation was obtained for dataset 3. Here, two patients reported, patient 1 with a left insular frontal lesion and patient 2 with a temporoparietal left lesion. We can see for patient 1, the lowest scores were reported in the motor functions. Here in the radar prod, in red, the prediction obtained with the formula that I showed you before, and the measure scored, and the outside ring summarized the scores within the different domains. Whereas for patient 2, the lowest scores were reported for the language domain. And you can appreciate the comparison between the measure scored and the prediction across these two patients. Overall, the mean absolute error of prediction was of 16.1% with respect to the maximum scores obtained. Here, the web application interface. I also leave you the QR code. You can run the application in any browsers, so on a phone or on a computer. Here, the scores that you can predict, for example, for the motor functions. And if you go to calculate, you can upload your disconnectome file for one patient. Here I'm uploading the file that you can download as an example from the website. And then the prediction now are running, and you will see that the results will be displayed in the web application interface. It takes less than 1 minute, and here the UMAP coordinates that summarize the disconnectome and the predicted scores. You can download the file as a CSV file and use it for further analysis on your computer. So in conclusion, we use the low dimensionality techniques to summarize the disconnectome variability and to run neuropsychological scores. We correlated the neuroimaging data acquired within 1-2 weeks with the neuropsychological scores at 1 year. Then a white matter atlas allows us to visualize in the neuroimaging space the results obtained in the embedding space. Then a web application allows a broader validation of the model. Indeed, it's possible to run freely the model on your own data. So try it if you like it. And finally, I would like to thank you for the attention. And of course, I would like to thank all my collaborators that made this project possible.